Hello. Here we talk about some special types of permutations and the general result about all permutations. Special type will be called cyclic permutations or cycles. And the general result will be saying that any permutation is a product of such. They're called independent cycles because they will be operating on different elements. So let's start with defining a cyclic permutation. Let's imagine that we're permuting an element, so we're in this set or group of permutations of n things. And let's imagine that we have really only L elements permuted among our n elements. They don't have to be the first L, they can be just some randomly scattered inside our n elements. So let's call them I1, I2, up to IL. And let's imagine a permutation which moves them this way. So the first in the list goes to the second to the third, one before the last goes to the last, and the last is pushed inevitably back to the beginning of the list. So that is what is called a cycle. A cycle on this set of numbers. So these numbers I1 up to IL are some numbers inside our n elements, are some elements. So this is a cycle, and that is a compact notation for it, not to write it as a table or draw a picture of it. So here's a general fact about a theorem about any permutation. That it is possible to write it as a product of independent cycles. So by independent I mean that the sets on which they operate do not intersect, that they do not permute the same elements, different cycles in this decomposition. And I will leave a space for the proof, and it will be really short, so here will be the end of it. And before giving a scientific proof, an argument, well, outline for that argument, I would rather examine how it works on a concrete example for a concrete permutation. So let's imagine a permutation. Let's draw it, record it as a table of values, and let's imagine that we're permuting 9 elements, not to go to double digits. And all we need to do is to list some answers and list the answers, and the answers will have to be all different, non-repeating. So let's put 3 here, 5, 1, 7, 4, 9, 2, 6, 8. Nothing is repeating, so that looks like a permutation. Now I have to produce a decomposition into the product of independent cycles of things which of permutations which themselves shuffle elements in the cyclic pattern. And the way we do it is easy. We just start with the first of our permuted elements at all and see where it goes. And it is mapped into 3. So yeah, that's the pattern. 3 is mapped back into 1. That's the end of the length 2 cycle, what is called transposition as well. So 1 and 3 are transposed into each other. Let's then open the next cycle, which will start with the first thing which is not already recorded. So 2 goes into 5, 5 is sent into 4, 4 into 7, 7 back into 2, close the cycle. Now the cycle has length 4. And we continue with, again, starting with the first thing which is not already in cycles. So 2, 3, 4, 5, 6. 6 goes into 9, and 9 goes into 8, and 8, yeah, no other place, but I have to go back to 6. So we have it completed, the decomposition into independent cycles. Yeah, you see how it goes. I will now try to make a general argument which will work for all permutations independently. It will be with this general scientific sort of trick of using equivalence relations. Let's imagine a permutation we are decomposing into independent cycles. So take some permutation sigma, and how to see these sets on which these independent cycles operate? Well, the answer is easy. So introduce an equivalence relation. On the permuted elements, which will group things according to cycles. So let's just say that two elements from our n-element set are equivalent if there is some iterate of our permutation which moves the first into the second. Please check that this is an equivalence relation. 3 properties of equivalence relation are satisfied by this. And then check that equivalence classes are what we saw as independent cycles. Well, independent they become because equivalence classes do not intersect. There will be these sets on which these independent cycles operate, and then on each such set, by the definition of our equivalence, we will have to have this cyclic pattern, because if we choose one in this equivalence class, then any other will be seen as a result of iterate of our sigma. And so we could see what is the first iterate, the second, and so on, and we have to go back to the beginning because I only have finite number of possibilities at all. So that is it. Let me finish with an argument, a justification of why it is of practical, it could be of practical interest. So let's, for example, let's imagine a situation where we are computing large iterate of the sigma. So let's imagine, say, power of 145 for that sigma we want to compute. And yeah, by some practical reason, what we can observe is that each cycle repeated as many times as its length will be the identity. So if we forget about the rest of the cyclic decomposition, look at one cycle. So this length 3 cycle, repeating it 3 times, iterating it 3 times will be doing nothing, because on the second iterate 6 will go to 8, 8 will go to 9, and 9 will go to 6, and on the third iterate the things will just stay where they are, because we'll have to iterate 1, 2 and 3 times, and 6 will go back to itself, and so is the other 2. So it's easy to see, say, in this picture, that if you iterate it as many times as the length, you will be not moving your elements at all. So that is saying that that is really first step in saying that the order of any cycle, the minimal number of iterates, which is the identity, is just the length. Well, I would just argue that nth power is the identity, but you could see that any smaller power will not be, because if you're iterating less than L times, I1 will go somewhere in the list but not back to itself. So you could say that the order of any cycle doesn't matter what is in it, as long as the length is L, the order will be L. So the order of this transposition is 2, iterated twice is the identity. The order of this 4 cycle is 4, and the order of this 3 cycle is 3. And what is the smallest number of iterates we have to perform the whole thing to get the identity? Well, you can imagine that it should be the least common multiple, because these permutations are independent. Their powers, when we compute their powers, let me write it somewhere here, like say for this one, it will be possible to write it as the power of the transposition, the power of the 4 cycle independently, and then the power of the 3 cycle. So we could see what happens, or we could see a generic cycling behavior for that permutation. What is the smallest power which is equal to the identity? So that smallest power will have to be divisible by 2, divisible by 4, and divisible by 3 simultaneously. It has to be the least common multiple. The order of sigma has to be the least common multiple of the length of independent cycles. 2 and 4 and 3. And that is 12. And so 144 is 12 times 12. So after you do 12 times, you don't care, because it will any multiple of 12 will still be giving us identity. So that can be seen to be equal to the original sigma. That iterate, you can argue it separately in each of these independent cycles channels. That iterate will be just the transposition 1,3 itself. That iterate, that power will be just the 4 cycle, and so is for the 3 cycle. That power for the 3 cycle will be just the 3 cycle itself, just the original 3 cycles. So altogether you'll have your sigma back. That's one reason why orders of permutations could be good to know. That's it for today. See you later.